Alrighty, if you're in Zoom, please type something into the chat to let me know that you're here. The roll sheet is being distributed to those folks who are attending the class in person. So today we are going to finish up our discussion on common base amplifiers, where I believe we left off about to begin common base amplifiers with a source resistance and with a base resistance. So let me just check where I'm at here. So that's emitter generation, base resistance. Then we did source resistance, yeah. So we need source resistance and base resistance now. All right. Make sure these are all just people saying that they are here. And it appears that that is the case. All right. So common base with and base resistance. All right. So with both a source resistance and base resistance in our circuit, we're going to have something that looks like this. Here is our input voltage. Over here, we have some base resistance, RB. We have a bias voltage applied, and we are still taking our output at the collector terminal because that's what we do when we have a common base amplifier. Sorry, let me just pop over here to chat. All right. So let's figure out what our amplifier parameters are for this particular configuration. Starting with our input resistance as usual. So in this particular circuit, if I turn everything off that needs to be off, it should look fairly familiar. RC, RS, and RB. So if we just look in, sorry, and let me write, here's where we're looking in. So we're trying to find Rn from this perspective. So if we look in from here, specifically, let's call this guy Rn prime. Let me open up another file real quick. And I think this is the one I'm looking for. So what I believe I've just opened up, and I'll have to go through here and check, is my common emitter amplifier configurations. Yeah. So I want my common emitter with a base resistance. Sorry, let me find that real quick. All right, so I would argue that looking in through this specific terminal where I've labeled it as green, the collector terminal, this guy. So we're kind of looking past that resistance RS. We're going to see it in series with, I would argue, a common emitter amplifier with emitter degeneration and base resistance where RE is infinitely large, meaning we have an open circuit there, right? And so if we have RE as an open circuit, hold on, let me find this real quick. Where am I? Yeah. Common emitter with emitter degeneration and base resistance with RE is equal to infinity, but we're looking in through the emitter terminal. Sorry, I may have looking in through the emitter terminal. Sorry, I think I wrote down the wrong amplifier here. The reason why I'm saying that is because for the common emitter amplifier here that I'm saying it looks like, we're looking in through the base terminal, and we're definitely not looking in through the base terminal when we're looking at a common emitter, right? We're always looking in through the collector terminal for our input voltage. So I apparently have a mistake, not a problem. We can figure out what's going on here pretty easily. All right, so scratch that thought real quick. Let's look through my common base amplifiers to see if this looks like anything that I've seen. This is the one that I'm working on right now. I need to turn that off or we're just going to get in the way. Here we go. Okay, so it looks like a common base amplifier with emitter degeneration where RE is equal to infinity. So I just wrote CE instead of CB, right? So if RE is equal to infinity, we have the exact same thing. So I apologize for that confusion there. So I can see if I look at my input impedance, when RE is an open circuit, 1 over an infinitely large resistance, that term goes away, and I'll simply have the reciprocal of beta plus 1 over R pi plus RB. So that means that, come all the way back down here, this Rn, seen from this point in the circuit, is R pi plus RB over beta plus 1, and therefore our total input resistance for this guy is simply RS plus R pi plus RB over beta 1. A note on my paper notes to fix that mistake real quick. Common base. All right. For our output impedance, we're looking at this circuit. Here is RS. Here is RB. Here is RC. We're looking in through this terminal. And so I would argue that this guy does look like a common emitter amplifier with emitter degeneration and base resistance, right? So when we're calculating the output impedance of a common emitter amplifier, let's see what's in chat. Okay. When we're looking at this particular circuit from the output resistance perspective, Vn, as it's labeled here, would be connected to ground, and the opposite leg, or the bottom leg of the resistor connected to, or the bottom leg of the resistor Re, which in this place is playing the role of Rs, is also grounded out. So this is exactly identical to this guy, right? And so from that, our out is going to be the exact same thing as we saw there, which we have listed as simply RC. Same as CE with ED and base resistance. All right. So finally, we need to look at our voltage gain, and this is where things are a little unfamiliar. So we will have to apply our small signal model. Let's see, R pi, V pi, GM V pi. Here's our emitter. Between our emitter and ground, we have our resistance RS as well as our voltage source Vn. Between our base terminal and ground, we have our resistance RB. And between our collector terminal and ground, we have our resistance RC. And we're taking our output at the collector, so that means here is the out. All right, so we should easily be able to see that V out is equal to negative GM V pi times RC, and we can rearrange this expression to find that V pi is equal to negative V out divided by GM times RC. We all okay with that amount of algebra? What I'm going to do now is I'm going to find the voltage present at my emitter terminal with respect to ground. So The voltage present at my emitter terminal with respect to ground using Kirchhoff's voltage law around this loop, where I'm going to define this guy as VE. I see that VE will be equal to negative V pi plus the voltage drop over my resistor RB, which using Ohm's law is going to be RB times negative V pi over R pi. I'm now going to substitute in my relationship for V pi. And so I'm going to have negative V out over GM RC. And I'm going to multiply this term by a factor of R pi over R pi because I'm going to combine it with something else in a step in a minute. So I just want to be clear about what's going on there. Plus negative V out over GM RC. And I have a factor of RB over R pi here. And so I can see then that VE is equal to V out positive because there is a, So I factor out V out, I'll have that there. And then I'm going to have a common factor of GM times RC times R pi in my denominator. Well, GM times R pi is simply beta. So I'm going to call this guy beta RC and multiply this guy by R pi plus RB. Now, if I use Kirchhoff's current law, I can see that the current flowing through my source resistance is VE minus VN over RS, and this has to be equal to the current. So I'm saying this current is equal to this current plus this current. So I'm going to have V pi over R pi plus GM V pi. I'm now going to substitute in my relationships for VE and V pi. This one gets lengthy. So RS. Yeah. So I'm saying the current that flows through my source resistance RS is the total voltage drop over RS divided by the resistance RS. I'm applying Kirchhoff's current law at the emitter here, to be specific, okay? All right, so I will have V out divided by beta RC times R pi plus RB minus VN, all divided by RS, equal to, I'm going to factor out V pi here, so I'm going to have negative V out over GM RC multiplied by a factor of 1 over R pi plus GM. which gives me negative V out over GMRC times beta plus 1 over R pi. Finally giving me negative V out over RC multiplied by a factor of beta plus 1 over beta. I'm done manipulating the right-hand side. I'm simply using the relationships that 1 over R pi is equal to GM over beta. That's where that introduction of the beta term came from. If I look at so now what I'm going to do is I am going to attempt to put all of my V out terms on one side of the equation, all my V in terms on the other side of the equation. So this will give me, let's move this down one so I don't run into trouble here. V out divided by beta RC RS times R pi plus RB. So when I divide this guy right here by RS, that's just putting that factor of RS into the denominator of that fraction, just to be clear there. Plus V out over beta RC. And so what I'm going to do right here is multiply by RS over RS so that I have a common denominator. So that's me moving this term from the right hand of the right-hand side of the equal sign to the left-hand side of the equal sign and multiplying by a factor of RS over RS. Just to be clear, will be equal to Vn over RS. And so I can now see that there is a common factor of RS on every term on the left-hand side of the equation and every term on the right-hand side of the equation, which means I can just throw that guy away. And so that leaves me with V out is R pi plus RB plus RS times beta plus 1, all divided by beta RC is equal to Vn. And then from this, I can see that my voltage gain is simply the reciprocal of that large fraction there. Beta RC divided by R pi plus RB plus RS times beta plus 1. From this, we can see that the inclusion of a base resistance and a source resistance kind of serves to lower the overall voltage gain of our system, which brings us to our full bias circuit. So we can see from this equation that having RB in our circuit messes things up, right? Having some finite base resistance causes our gain to go down. And having some finite source resistance also causes our gain to decrease. So we are now going to implement capacitors into our circuit specifically to bypass those two guys. So our common base circuit with full bias is going to look something like this. Here's our resistance RC. Here we have an emitter degeneration resistance. Here's R1, and here's R2. This is VCC. So this is our traditional simple 4-resistor biasing network that we've been using for everything, right? So our goal here is to bypass a base resistance. So in order to do that, I'm going to put a capacitor explicitly in parallel. I'm going to call this guy CB with resistor R2. I could put the capacitor between the base and VCC as well if I wanted to. It would have the exact same small signal effect, right? So for large signal analysis, CB is an open circuit. My bias point is well established, nothing to screw with too much. With the AC analysis, that capacitor CB becomes what? A short circuit, which means that resistor R1 is between the AC ground of the power supply signal and the short circuit connected to ground of our capacitor, which means R1 is shorted out, right? R2 is also shorted out because it's directly in parallel with that short circuit. So we have effectively completely eliminated our base resistance by putting that one capacitor in that particular configuration. So we get rid of that large term that's lowering our gain. On the source side of things, fairly straightforward. We put in a capacitor. Let's see. Like so. And so we're still going to see our source resistance. We really can't get away from that. But we have to make sure that we have that emitter degeneration resistor there to ensure that our DC biasing conditions has a path to ground for the emitter current so that it's not always set to be exactly equal to 0. So this is what our common base with full bias circuit looks like. Looks suspiciously like one of your homework problems, I think. To analyze this guy, we can use a simplified small signal model. So let's say, here's my power supply rail. Here's my resistor RC. Over here, I'm taking my output. Here's my degeneration resistor RE. Here is my source resistance RS. So that big ugly circuit simply reduces to this guy, what should be fairly straightforward to analyze, right? I'm going to call this node right here, or give it a nodal voltage VE that we'll use in a minute to calculate our voltage gain. But from an input resistance perspective, what we see is here's our resistor RS, here's our resistor RE, and then we're going to see between that node E and ground the input resistance of our common base core amplifier. So we're just looking in through this terminal and we see a common base core, right? Vn is on the Vn prime, let's call it, is on the emitter terminal. V out is on the collector terminal, and we have some resistance between the collector and our power supply. So simple common base core. So that means that we see a resistance of 1/GM representing the input resistance of the common base core. So this gives us simply RS plus RE in parallel with 1/GM as our input resistance for our full bias circuit. Easy enough, right? For our output resistance, we would see when we short out Vn that RS and RE are simply in parallel. So we would have a common base amplifier with emitter degeneration, where our emitter is degenerated by a parallel combination of RS and RE. Which means our out is once again simply RC. Our voltage gain, we know that V out over VE multiplied by VE over Vn should give us our overall voltage gain. So we're just breaking it up into two stages like we've done every time we've looked at our full bias circuit. So V out over VE is GMRC. And then we're going to simply apply voltage division to find this voltage VE, which is the voltage drop over RE in parallel with 1/GM. So to me then, that means we're going to have RE in parallel with 1/GM divided by RS plus RE in parallel with 1/GM. And that is our overall voltage gain for our circuit. So all the groundwork we did really made analyzing our full bias circuit fairly trivial, which is kind of the point. All right, so let's see, it's 8:35. So our last amplifier topology that we need to talk about, and this one is going to be a much shorter analysis, is the common collector or emitter follower amplifier. All right. So the base version of this amplifier, or the most simplistic model, would be something like this. We connect our collector directly to our power supply voltage. We take our output at our emitter terminal. Between the emitter terminal and ground, we have some resistance, RE. And then we are going to apply our input signal at our base. So this is our generic model for a common collector or emitter follower amplifier. So for our amplifier parameters, let's look first at our input impedance. So from a small signal perspective, we're going to have something like this. E. And I believe, you guys can tell me if I'm wrong here, that this, well, actually, I was going to say it looks pretty similar to a common, it looks very similar to a common emitter amplifier with emitter degeneration, where RC is a short circuit, right? Because we're connecting our collector directly to ground. So with that in mind, let's circle back over here to our common emitter amplifiers, all right? So we want common emitter with emitter degeneration. And we are taking our input impedance. So the location of our output pin here does not matter because we're just considering our output to be an open circuit. So that doesn't matter at all. And we have RC is equal to 0. But RC doesn't actually even show up in our input impedance calculation at all, right? So should be fairly straightforward to see then that Rn for our emitter follower is the exact same as we have here, simply R pi plus 1 plus beta Re. For our output impedance, circuit that we're looking at, is this guy. We're taking our output at the emitter terminal. since we're taking our output at the emitter terminal, we shouldn't have any other circuits that look like this. This is the only one we've ever taken the output specifically at the emitter terminal. So we are going to need to apply our small signal model here, I believe. So let's do just that. No, because we should see it's going to wind up looking like RE in parallel with something else, right? And so let me explain what I mean by that. We're going to see something this way, but we're also could potentially see something in the up direction. So we might see some internal resistance of the transistor itself. So it might be related to R pi, something like that, okay? So we can't just say, well, it's RE, because there's another path to ground that our signal could take. We need to take that into account. So I'm gonna draw my small signal model for this guy. So let's put our base here. Here is R pi, B pi, GM, V pi. Here's our emitter terminal. Here is our collector. All right, and then down here is what I'm going to call a ground rail. All right, so between the emitter and ground, I have my resistance RE. So let's put this guy right here. But because I'm trying to find my output resistance, that's also where I'm going to place my test source. So it will be connected between the emitter and ground. So I'm going to throw this guy right here, call him Vx. Here's my current of interest, Ix. Between the base and ground, I have a short circuit. And between the collector and ground, I have a short circuit. So if I redraw this guy in my standard circuits 1 methodology, putting my test source on the left-hand side, where this node represents my emitter, this node down here represents ground, I have RE placed directly in parallel with my source. R pi will also be placed in parallel with my source. And the positive polarity terminal is connected to ground. The negative polarity terminal is connected up here. So this is my definition for V pi. And then in parallel with that, I'm also going to have my current source, where my current is flowing from the collector, which is shorted to ground, to the emitter. So that's why it's flowing in the direction indicated. And here we have GM V pi. So if I apply Kirchhoff's current law at my top node, I can see that Ix is simply Vx divided by the resistance Re plus Vx divided by the resistance R pi minus GM times V pi, where V pi is exactly equal to negative Vx, And then from this, my output resistance is simply 1 over Re plus 1 over R pi plus GM all to the -1 power. So from the output terminal, I see Re in parallel with 1 over R pi in parallel with GM. So it's not just as simple as saying, well, it's Re because it looks like it might be Re, right? So let's take a moment here to talk about the size or scale of my input impedance, right? So Rn is R pi, something on the order of a few kiloohms, plus 1 plus beta times Re. So what can we say about this input impedance? Generally speaking, it's going to be fairly large, right? Our output impedance represents 3 resistances in parallel. So generally speaking, we should expect that guy to be pretty dang small, right? So we have very high input impedance, very low output impedance. So far, things are looking pretty great. If we look at our voltage gain, here's where things get a little weird. So I'm going to use the small signal model. Here's our base. Here's our emitter. Here's our emitter resistor, Re, over which we are taking our output voltage. We are applying our input voltage to our base. And because our collector is connected directly to our power supply voltage, we short that guy out. All right, so let's start by writing an equation for V out. So V out should be the resistor Re multiplied by whatever current will flow through that resistor Re. There will be 2 contributions, the current flowing through the resistor R pi plus the current being supplied by our dependent source, right? Those 2 guys are going to combine and flow through our resistor Re. So I'm going to express that as V pi over R pi plus GM V pi. And I'm going to do a little bit of algebraic manipulation here. So I could factor out a common term of V pi. So this would give me V pi times Re times 1 over R pi plus GM. Looks like V pi Re GM times beta plus 1 over beta. I can solve then for V pi, and it will simply be V out divided by Re times R pi over beta plus 1. Using Kirchhoff's voltage law, I can see pretty easily that Vn is just V pi plus V out. All right, let's scroll up here. Should be fairly trivial to see that Vn, our input voltage, is then simply V pi plus V out. And so we can see something about the voltage gain actually already here, right? If Vn is equal to V pi plus V out, then that means the output voltage, by definition, is always smaller than the input voltage. So in some sense, a common emitter amplifier, common collector amplifier or emitter follower amplifier is a fancy voltage divider. Really, inherently, that's what it's doing. It's a fancy voltage divider with very high input impedance and very low output impedance, which we would consider a buffer, okay? So it plays the role in BJT amplifier circuits that a buffer amplifier plays in op-amp circuits, where a buffer amplifier is a non-inverting amplifier with a gain very close to 1, so that the output almost exactly follows the input. Well, here we're going to see that the output will almost exactly follow the input as well. So it's just a much more simple way to have that same circuit capability if you're considering the complexity of the internal circuitry of an operational amplifier. Okay. All right, so that out of the way. I can if I substitute in my relationship for V pi, I get V out times 1 plus R pi over beta plus 1 times factor of 1 over RE. And from this, my voltage gain is simply 1 over 1 plus R pi over beta times 1 over RE, which is the same as RE divided by RE plus R pi over beta plus 1. All right, so our next step is traditionally to figure out what's going on if we include the early effect. So let's swing back here to our original model, okay? So what happens when the early effect is included? We would place, I'm going to draw it in blue. A resistor R0 between the collector and the emitter, right? That's inherently what the early effect does, represents that change in collector current due to variations in VCE. We model that with a resistor placed between the collector and the emitter. Well, for all of our small signal analysis, where is that resistor R0 going to be placed? In parallel with RE, right? Because one leg of the resistor is connected to the emitter node, and the other leg is connected to VCC, which is an AC ground. So there's where R0 would be. So how does that influence our input impedance? Thoughts? When we put a resistor in parallel, what's going to change? We're going to have RE in parallel with R0. How is it going to influence our output impedance? We're just going to have a factor of 1 over R0 in here because it's in parallel with RE. So I'm going to put RE in parallel with R0 there. What about our voltage gain? Oh no, RE in parallel with R0. Everywhere we see RE, we just put it in parallel with R0 and we're good. We don't need to do any further analysis. So early effect taken care of. This is probably the easiest circuit to analyze what the early effect does. All right. Don't need those two. So let's move on to emitter follower with a base or source resistance, because since we're applying our input at the base, this could be representative of our biasing resistors, our resistive divider network, and or some source resistance internal to our voltage source VM. So our circuit would look something like this. And I'm going to say that we have some resistance RB right there. Here is the So let's start with our input impedance. Who can tell me what it's going to be? Or at a minimum of what it looks like. How is this remotely different than what we just did? Let's start there. What's the only difference here? There's a base resistance. How is that base resistance connected to the circuit we just analyzed? It's in series with it. So I would argue then that Rn is just Rb, our base resistance, plus whatever our other input resistance was, which was R pi plus beta plus 1 Re, if I'm not mistaken. No real need for analysis necessary. You can just look at this thing and tell what's going on. For our output resistance, unfortunately, it won't be quite that simple. So I'm going to look up here real quick where we calculated our output impedance. So if we had a resistor RB placed between our base terminal and ground, where would that show up in our small signal model analysis? So it would be between the base and the ground. So we would see that this guy, R pi, is in series with that base resistance, RB, right? So I'm just going to redraw this second model with RB in series with R pi. So here we have RE. Here we'll have R pi plus minus V pi. Here we have RB. GM V pi. So if I do Kirchhoff's current law at the top node, I can see that Ix is Vx over Re plus Vx divided by R pi plus Rb minus Gm V pi, where V pi is negative Vx R pi over R pi plus Rb using voltage division. Anybody got any problem with that? So this means that Ix is equal to Vx multiplied by a factor of 1 over Re plus 1 over R pi plus Rb plus Gm R pi, which is beta, over R pi plus Rb. And from there, our output resistance is just 1 over Re plus beta plus 1 over R pi plus Rb to the minus 1 power. Lastly, we are going to have our voltage gain. So I'm going to step up here to our original circuit real quick and call the voltage directly at our base, some voltage VB, so that we can break this guy up into 2 stages. So we are going to see that the voltage gain is going to be V out divided by VB, which is just the gain of our base emitter follower configuration, multiplied by the relationship between VB divided by Vn, which we should be able to get just using simple voltage division rules, right? So with that in mind, our voltage gain AV is V out divided by VB multiplied by VB over Vn. Well, V out over VB was Re over Re plus R pi over beta plus 1. Okay. What I'm going to do just real quick here is I'm going to multiply the numerator and denominator by a factor of beta plus 1, which is going to give me beta plus 1 right here. Get rid of that fraction. So, exact same gain, I've just multiplied by a factor of 1, expressed as beta plus 1 over beta plus 1, and it'll be pretty obvious why I'm doing that in just a second. So now, we're going to use voltage division, okay? So what's going on here? I got room to do it right here. So here's my input signal. I have my resistance RB. Here's my voltage VB. And then between that node and ground, I see the input resistance of our common collector amplifier base model, right? It's exactly how we found the input resistance to begin with. So this guy should be R pi plus beta plus 1 Re. So if I wanted to find that voltage VB specifically, I could just use voltage division. And so that means I'm going to have a numerator of R pi plus beta plus 1 Re divided by Rb plus R pi plus beta plus 1 RE. And I can see that the denominator of my first term is identical to the numerator of my second term, so those guys cancel each other out. And that leaves me with RE beta plus 1 divided by R pi plus RB plus RE times beta plus 1. So there's my voltage gain. Easy enough to follow. So our base resistance here does serve to decrease our voltage gain by some factor. All right, so our last thing to look at then is our emitter follower with a full bias circuit. So that's going to look something. Here's R1. Here's R2. RE. Out. And usually RB and BN. Excuse me, let's call this RS and BN. All right, so this arguably looks complicated, but we can use a simplified small signal circuit to realize that it's really something pretty familiar. So for instance, at a small signal model level, how are the resistors R1 and R2 connected? So small signal model VCC becomes ground, which means both R1 and R2 are placed between the base and the ground, right? So we would see them as in parallel. So small signal model, simplified version, would look something like this, where we have our source resistance RS, here is R1 in parallel with R2, here's RE, and here's V out. So it just looks like a resistor network connected to our emitter follower baseline model, right? Which is literally exactly what we just solved. We're just representing that entire resistor network by this one resistor RB here. So do we actually need to buy for the input impedance, output impedance, or voltage gain when we could just see that VB, from a Thevenin perspective, would be RS in parallel with R1 in parallel with R2. And there we go. That's it. All right. So there was one topic. Well, we got 5 minutes. Okay. At the very beginning of our review section on Wednesday, I'm going to spend 10 to 15 minutes talking about the concept of intrinsic gain in an amplifier, because that's something that I skipped over earlier, and Dr. Batari wrote a question specifically asking about that, so I figure I better cover it so that not all of you miss it. Very abbreviated version of intrinsic gain is just the gain of an amplifier circuit where it's unloaded, meaning if we looked at an emitter follower circuit, we would be figuring out what the gain is when RC approaches infinity. Something like that. We're literally saying disconnect all the biasing resistors and tell me what the gain of the network is. So it's a fairly straightforward topic. Won't take a couple of minutes to go through. I just don't know that I can do it in the 4 minutes we have left. So we'll talk about that at the very beginning of class. Maybe work a couple of numerical problems just for the sake of argument, since we haven't worked a whole heck of a lot of those. And then I think that'll probably be a fairly good review. So anybody got any other questions or topics or anything that they can think of that they'd like me to talk about at length on Wednesday?
I'll think of a better question for it, but just the way to like
Sure, absolutely. So, 100%. So what I'll do later on today or tomorrow is develop, I'll say, 2 circuits. Similar to what you would expect to find on the test, and ask you questions like what you would expect to find on the test. And we could talk about how we could look at those relatively quickly to say, all right, so what is it that I'm being asked and how would I best go about calculating that and stuff like that. Honestly, a lot of that is going to be able to draw a small signal simplified circuit quickly and a large signal simplified circuit, meaning with all your capacitors open circuits, what's left over and what does it look like. But we can definitely cover that on Wednesday to work a couple of numerical problems. All right, that sounds like a good plan to me. So I will see you guys on Wednesday. I do have all but I think 4 of your exam 1s graded. So expect those grades to be posted probably later today. I'm going to try to get, your bonus quiz for exam 1 graded today as well. So I'll send those grades out. I'm not sure when I'm going to get to the project. There's also going to be a bonus quiz for this exam. That's going to be posted today on Moodle as well. Before the exam. Dr. Batari made it out. It's 1 problem. It's fairly straightforward. It's 1 numerical analysis problem. All right. See you guys on Wednesday.